Let's get started, everyone. So we have a good crowd. I'm surprised that at the end of the semester, I was thinking that people would be vanishing and disappearing. So it's a great pleasure to have our very own Mike Pritchard. He's actually part of the LEAP Center. Long story short, so now he's an associate professor at UCI Urban, actually only part of the time, and became last year. Actually, we were discussing that last June. Actually, he moved to NVIDIA as well, so 80% of the time right now, where he's director of climate simulation research, and he's been going to be talking about that. So Mike started at UCSD, and he told me the funny story that at the time he was about to start his PhD in Toronto, and then someone told him, you know what, you can actually learn the exact same equations with just by the beach in San Diego. So that's how everything started. And then we met like randomly at a DOE meeting, reviewing some proposals, started to talk about clouds and things. And I remember at Christmas time, I was getting really frustrated with the convective parameterization. I said, and I called Mike, said, you know what, maybe we can do better, using machine learning. And that's how we became kind of partners in crime in that area. And since then, he's been doing it. Oh. Oh, really? No, not this one either. Okay, I'll be quick anyways. So yeah, so it's a great pleasure to have Mike today, and he's going to be telling us about all of the exciting things going on in his group, and also in NVIDIA. There's a lot going on right there. So great to have you here. Thank you.
Thanks, Pierre. That was super sweet. Yeah, that was a life-changing email. Yeah, so thanks so much. Thanks so much for coming. I'm going to, let's see, learn how to advance my slides. Does this work? Hey, there we go. Okay, yeah. So I want to acknowledge my conflict of interest, kind of wearing two hats right now. We'll divide it up cleanly, despite the NVIDIA slides. First part is going to be all about LEAP and UCI. And then I'll spend maybe 10 minutes at the end talking about NVIDIA stuff, but I especially want to talk about the work that we're doing because of LEAP, that's been enabled by LEAP here. So let's jump right in there. So a bit about me. I've been interested in two things that kind of have attention here throughout my academic career. I think global climate dynamics are beautiful. For their own sake, planetary fluid dynamics, these questions about how will cloud patterns reorganize as the planet warms over the remote ocean are beautiful on the one hand, but they're also really important to us as people. Half of me is just as concerned with what's going to happen for my kids, how the water cycle is going to change in the future, it's the multiple geographic regions that may be stressed with water hazard and geopolitical migrations, etc. So yeah, I found both of those interests tend to coincide around these computational issues of confronting turbulence with computers. People live in a turbulent boundary layer. The water cycle dynamics are highly turbulent. Turbulence is under-resolved in climate models. And yeah, I guess this lack of explicit sub-kilometer physics in climate models today is something that should keep us up at night, or at least has worried me for a long time. And because of that, I really like to explore big supercomputers. We live in I'm from Canada originally, and I came down here and discovered the scale of US cyber infrastructure, and it's just amazing, but it still is not enough. Climate scientists bring supercomputers to their knees, and because the phenomena, it's an audacious task. The phenomena span 8 to 10 orders of magnitude in time that matter, and you're just not going to simulate it all the stuff that matters. Okay, so, oh, sorry, that didn't come through. Yeah, in academia, I've mostly tried to cope with a particular algorithm that I want to tell you a bit about, because it's going to inform most of the first half of this talk, which is called MMF, the multi-scale modeling framework. It's one of many ways to cope with not enough resolution in climate models. Some people embed high resolution over their country as a coping mechanism. That's nice because it's got lots of geographic detail about your mountains, etc., but it's not global. Superparameterization, which is also called multi-scale modeling framework, decides to embed small samples of explicit convection within each grid cell of a conventional planetary model. So imagine like 10,000 micromodels, each of which is subcycling with a really fast time step and making explicit clouds and convection living within a predictor-corrector relationship with a large-scale model that knows nothing about convection. And the way the system works is that the planetary model chugs along in time, updates its state vector, so you get a new temperature profile, a new moisture profile, but it didn't know about convection. The micromodel feels that tendency, but convects in response to it, it goes somewhere different. And because the convection is all localized and periodic, it turns out that this approach has allowed for really convenient arteries for machine learning, because there's very clean scale separation in the way this strange coping mechanism has been designed. So yeah, that's the MMF, and that's been my playground for 10 or 15 years, my area of expertise. And it's also what, can I remove this thing somehow? Okay, let's see. So it's also been my journey to artificial intelligence. It's learning the arteries of that scale interaction. So that's using deep learning, which is just, better than human software that can learn from many examples of data to produce remarkable mappings. That is powered by GPUs. It's like regression, right? Multi-dimensional, high-dimensional regression. So deep learning is just, find f given x and y. So the inputs can be very high dimensional. In my case, those inputs are going to be that large scale model that didn't know about convection at some location in space. What's the temperature vertical structure? What's the moisture vertical structure? What's the incoming sunlight? What are the incoming heat fluxes? And the outputs will be, what did convection do in response? How did the moisture change? How did the temperature change? How did convection vertically redistribute mass and moisture? And how did radiation interact with that to result in a new temperature profile? Okay, so do we get the idea? It's one-dimensional, temperature in, moisture in, heating out, moistening out. That's the mapping I'll be concerned with. So of course, we're all blessed with the fact, like manna from heaven, that we have GPU accelerated, beautifully engineered software stacks now to do this sort of mapping. It's all powered by GPUs, so it's fun to work at a company that makes GPUs now. I remember, just anecdotally, my student Griffin Moores 5 years ago bought him a brand new MacBook, and he started to do one of these problems, and it started consuming power faster than the supply could deliver it when he hit .train, because it was trying to explore all the available hardware. And then we plugged it into a GPU and things got better. Okay, but yeah, this gets back to Pierre's comment about this email that kind of changed my life. When in 2017, he was like, I think we can do better with convection parameterization with machine learning. And we realized that we could use this multi-scale modeling approach to try to test this idea. We could take a simple test bed, remove some complexity, no continents, no seasons, keep it kind of simple, but keep a lot of complexity, really stochastic physics, convection, radiation, microphysics, fluxes, and create a beautiful training data set, hundreds of millions of double precision samples, input-output pairs, and then ask ourselves, could these crude sheets of dumb digital neurons learn the essential physics of the PDEs inside these micromodels? That was the exercise. And at first, very skeptical, right? You should be skeptical because it's just curve fitting on steroids. And anyone that's tried to fit a curve, should know that, oh, that animation doesn't work, darn it. Extrapolation's a problem, curve fitting is imperfect. But this was the first result offline. So from that training data set that shook me a bit. This paper that Pierre led in 2018. And what you're looking at here is as we go up in the atmosphere from the South Pole to the North Pole, these blue regions are where that fit was good enough that it was explaining more than 80% of the variance of the actual data. And those are not, those are important regions because this is the middle of the troposphere in the intertropical convergence zone where convection couples to the planetary circulation, and in the middle of the storm tracks in the mid-latitudes where that skill is important as well. So there's clearly regions where it's not working, but it was starting to work in those regions, and that got me interested. And then this amazing guy, Stefan Rasp, came to UCI for a summer, and Pierre and I co-advised him on this. And it was, we worked for a long time, and he went deep and aggressive on the deep learning. And eventually we got this result. This is more important because this is taking that fit that was achieved with data, and then taking the machine learning model and actually implanting it inside the climate model. So ripping out the actual micro models and replacing them with 10,000 instances of the machine learned model, and then asking the coupled system to chug along. And so despite the imperfections of the fit, can the scale interactions, this time with the microscale being handled by pure AI, hang together a simulation? And so to ask ourselves if it works, we look at pictures like this. This is a 2D space-time Fourier transform that summarizes the variability of the tropical atmosphere. And there's patterns here that we look for called dispersion relationships like this that represent the aggregate effect of a particular type of motion that's coupled to convection called equatorial Kelvin waves. And this is something called the Madden-Julian oscillation. It's just a nice rich summary figure of how the convectively coupled atmosphere is supposed to behave if convection is realistic. And this is non-superparameterized models that look unrealistic. So anyway, the match between these two figures was the thing that really shook me. It was like, wow, this can work to the point that we can hang together a multi-year simulation and get reasonable dynamics. And now I'm really interested. There were still existential questions like, can you conserve mass and energy to meticulous precision? You must if you're going to be a climate scientist. And then this other brilliant guy, Tom Buechler, that Pierre and I co-advised, came up with a way to just make it so that the deep learning could never hallucinate a scenario that didn't conserve mass and energy just by mucking with the architecture to make it so. It's quite a general method, but yeah, it had remarkably little effect on the optimization skill, which surprised me. I thought maybe it would help, but in hindsight, there's not very many degrees of freedom of constraints, maybe 4, despite a relatively large degree of freedom, maybe 100 scalars in the input and output space. And now this brings me to the main purpose of today, which is the current frontier that we're working on with LEAP, which is controlling the prognostic error. So I told you a nice story, but it's been a very difficult to reproduce story. And so we got lucky, I think, in Rasp et al. And, you know, even minor variations on the theme, like making the embedded cloud resolving models a little bit bigger, we could never get it to work. And adding geography, could never get it to work. More often than not, what we see is that for inexplicable reasons and inexplicable places, our simulations blow up spectacularly when we rely on these emulated physics in the subgrid. So hybrid AI physics climate simulation is really challenging. Okay, so that brings me to the thing I was most excited to work about on, when LEAP started. And so I want to tell you a story about Jerry and Sungduk's work. So the big question is, how do the decisions we make in the formulation of our inputs and outputs and in the formulation of our machine learning architectures affect this downstream signal that we ultimately care about, the coupled hybrid error? And the problem, I think, right now is that signal is not well sampled at all in the literature. So there's a lot of people saying what they think matters, very little sampling to convince you. And it's just a logistics problem. It's a technical problem. You think about what it takes to run a climate model. It's a lot of work, and it's unglamorous work of the sort that doesn't normally get you the line items on your CV that academia rewards. And so I think it's logical there's not a lot of it. Logging into HPC systems, dealing with queues, doing hyperparameter tuning on the GPU cluster at sufficient scale to get a large set of architectures, linking all those architectures that are in Python world to your Fortran climate model, doing the integrations on the CPU partition of the cluster, managing all the output, deriving the statistics, all this context switching between different types of workflows. You add it up, and then you've got to rinse and repeat every time you want to try a new design decision or a new ML architecture decision. And of course, there's not going to be much of this type of work. It's really janky. So that was the problem we wanted to lean into with a bit of sustained funding that could enable it. And yeah, so I want to tell you about a new end-to-end pipeline enabled by this LEAP project. So industrial scale auto training to auto testing. And yeah, this is fully the work of Jerry Lin, LEAP funded PhD student, and Sungduk Yu, project scientist who's co-mentoring him. And the work tries to combine 5 tools that have emerged from Pierre and my and others' work on this problem over the past 3 years. I'll tell you about each of the elements. The first is that test bed I mentioned in the beginning. That's intentionally kind of simple, no continents, no seasons on the physical side, and kind of simple on the ML side intentionally. Just MLP models, simple ones, 2018 machine learning, no transformers, nothing else. The second is a prototype auto-tuning paradigm from a paper in 2021 by Jordan Ott, computer science student at UCI, with Pierre Baldi, who worked with us for some time. And this summarizes some work he did beginning in this direction, where he is at least making 50 to 100 prognostic tests involving 50 to 100 separate candidate neural networks. And so each of these lines tells you the error, worse is up, of a prognostic test that, and some of them are terrible, right? This is a log scale. It's 100 Kelvin mean tropospheric temperature error. It's stable, it can hang together a very bizarre state for a year, but stability is not the metric, error is. So, reassuringly, your offline fits, the better you get in the bluest colors. Maybe it's not a coincidence that the best prognostic errors were the deepest blue. But clearly there's a lot of spread here. There's a lot of variability. There's a lot of stuff worth sampling. But I think these error metrics that we converged on in this paper were a helpful tool. The other thing is then an extension of that auto-tuning paradigm that emerged in the last couple years. And here I want to emphasize that US cyber infrastructure again. So hopefully you all know that through the NSF, especially as part of an NSF-funded Science and Technology Center, you can apply to get access to a dozen or so supercomputers around the country with no grant and very little overhead, including like lots of GPUs on this Pittsburgh Supercomputer Center. And you can also apply, if you need it, for in-kind software engineering support if you have a task you don't know how to solve. And so we did that because we didn't know how to get this auto-tuning to play nice and really scale on the nation's computers. But we got a quarter of this guy's time for a year, and he helped us figure out how to do it. And Sungduck wrote a paper that you can read about where he explains how to do it if you're interested in, and applied it to a microphysics aerosol emulation problem. But that's another tool we can take advantage of. And then the other one was another really simple, crude tool to deal with the Python to Fortran interface. It's got limitations. It can only work with simple MLP models, but it's easy enough and lightweight enough that it's a good way to solve the coupling problem, called the Fortran-Keras bridge. Yeah, and then finally, a lot of elbow grease and hard work by Jerry, who's been very patient and willing to engage in slow, high-performance computing training and building all the kinds of bash and unit scripts you need to actually automate and pipeline these tools and link them together. So I want to acknowledge that work, but put together, I'm really excited about what we have now. So it's like a push-button tool that will launch hundreds of trainings and testings, and you can actually test ML design hypotheses at some statistical depth. So the way it works is you have a first phase of automated hyperparameter tuning that you launch on the GPU partition. It works its way through the queue. You get hundreds of machine learning model candidates. And then there's a little script to automatically link each of those to hundreds of separate prognostic runs that are handled on the CPU partition and auto harvest all the resulting statistics. And Jerry's gradually honed and automated this to the point where he can now turn around and experiment in about 4 days, including the queue latency, which is great. So, all right, let's get to some results. So let me spend a bit of time on this slide. So there's 4 ideas worth testing. This is where we started. So I mentioned the Raspadal problem has been kind of unstable, hard to reproduce. It used one decision that was made is that the way the moisture variable was formulated is in terms of specific humidity. Specific humidity is a wiggly target. You have the option of instead formulating your moisture variable on the input in relative humidity. The advantage there is that relative humidity is bounded in any climate. And so it's less prone to out of sample drift. If the coupled system starts to go somewhere outside the training set, you're going to be less exposed to those problems if you're using relative humidity on your input vector. So there's a few papers that have been making that point in the past couple of years. And so that's one choice that we can examine the consequences of. The other one is to expand the input vector. Climate models are really complicated. They're a million lines of code. It's easy you're going to miss a causatively relevant ingredient when you try an exercise like this. And we did. We realized in Raspadal and some others, we missed ozone. Ozone obviously matters for radiative transfer. It should be in the input vector. I don't know what else we missed, but ozone was definitely one of them. Convective memory. Superparameterization multi-scale modeling is interesting because that interior micromodel remembers where it was last time step. There's an inertia and a memory that's carried at the microscale. It's not purely local in time, unlike conventional parameterization. So you can begin to incorporate that by also expanding the input vector to include the outputs of the neural network one time step ago. And the fourth family is to try something that learns heating and moistening separately, rather than learning heating and moistening in the same output vector. They have kind of different distributions. It may be worth training separate MLP models on the separate output variables. Okay, so that's into the weeds a little bit, but those are the first tests that rose to the top of our mind when we decided what we wanted to investigate with this new machinery. People have been claiming these things matter in the literature. It has not been sampled enough to really know. Okay, so let's look at the offline results first. So what you're looking at here are the results of 400 member hyperparameter scans in each of these 4 families. So the baseline is in dark blue. What we call specific, that would be the baseline, the Raspidal kind of result. And so lower is better here. You want to have less offline error. And you can see here in the tail, the stabilized tail of the performant models, you've got, maybe a little bit more skill offline when you switch to relative humidity, maybe a little bit more even than when you expand the input vector. That's encouraging. A lot more when you get to the previous tendencies, which is interesting as well. You see that not just for the heating error, but for the moistening error offline. But of course, the ultimate test that matters is online. That's why we did all this pipelining work. So let's see how things change. Does it still go baseline, relative, previous tendencies when we go to the online metric? Let's have a look. Okay, that's hard to tell. That's a few thousand prognostic hybrid climate model tests, I think. Same colors apply here. I don't know if this look better on my laptop. Can you see anything? So how about that one that looked the best offline, the purple previous tendencies? Is it looking the best online? Maybe purple's hovering down here at the bottom of the error graph on the moisture. Definitely not over here though. You squint your eyes, this is hard to look at, right? Let's summarize it with some PDFs. Okay, so here, higher is worse. This is a log scale. Blue's the baseline, a lot of error. This is heating, this is moistening error. Okay, as we incorporate relative humidity, good things are happening. Prognostic error is going down a lot, log scale. There's a tight mode here, not just for heating, but also for moistening. That's encouraging. As we expand the inputs to include the ozone, the mode's kind of similar, but the left tail that kind of really matters to me, the best fits, is looking a bit better, maybe especially for moistening. As we further include the previous tendencies, maybe that's the best tail yet for the moistening, but not for the heating. Remember that drift? So this is complicated. A key point is there's a lot of dispersion in these PDFs. There's a lot of empirical uncertainty here. So the implications of that, you can kind of take this exercise and morph it and say, okay, what would it take? Let me say I've got a threshold that I care about that's like a threshold of operational viability. Let's say it's 2 Kelvin RMSC in the tropospheric mean state climate temperature, 1 gram per kilogram moisture. What's the chance that I will find one fit that meets those skill targets based on these distributions? And it's really different for the different architectures. So for the relative humidity, you're basically never going to find one. But for this test that included expanded inputs and previous tendencies, we can find one, but you've got to train at least 100 MLPs to have an 80% of chance. So I think this just speaks to the point that sampling is really important. That we need to lean into hyperparameter scans, at least with these simple MLP architectures to find a decent fit. Okay, the other thing that we're looking at, and this is kind of hot off the press, so I haven't fully processed it. I wanted to show you some research in motion. We can look at the bias structures in the top models. Okay, so each of the columns here is a top model, the top 5 models in these 3 families. The first family, relative humidity; second family, expanded inputs; third family, previous tendencies. And you can see right away, screaming off the plot, we've got a big stratosphere problem. Way too cold, stratospheric drift. It's inescapable. None of the architectures have solved it. So something's missing still. But then I'm reassured that there's some reproducibility in these bias attractors after all this sampling, that maybe we got a shot at actually having a stable enough statistical ground now to understand what's missing and what the cause is. Yeah.
What
Thanks.
have you replaced in the real GCM? Have you replaced radiated transfer? Have you
Yeah, sorry, I should have mentioned.
replaced
Yeah.
everything?
So the emulator is replacing radiative transfer and all of superparameterization, which itself assumes boundary layer turbulence and convection.
All the column fillings.
Essentially, the vast majority of the diabatic physics, yes. Yeah. You don't have to formulate it that way,
Right.
but that limit of most complexity is of most interest to me. Yeah. I think there's a subtle point here, when you're not coarse graining in time, you have the ability to split processes. As soon as you coarse grain in time, processes are mixed and you can't split them. And then you leave a bunch of compute acceleration potential on the table. So I'm really interested in the challenging problem of coarse graining in time and space, because that's where the biggest potential sidestepping of Moore's law that we all need can happen. Yeah, thank you. Okay, how am I doing for time? I lost track.
Yeah, 20 minutes then.
20 more minutes?
30.
30 more?
Yeah. Till the end. If 20, you.
Sweet, I'm going fast. Good. All right. Maybe I'll pause there in case any of that was unclear. Yeah, there was already one question.
In the spreads that you were showing, the different ensembles, was the randomness coming in just the initialization of the weights and the hyperparameters, or was the test data samples also randomly assigned?
I didn't explain the search. I'm sorry. Yeah. The things we search over randomly are, generic aspects of the architecture, the depth, the width of every node, of every layer. What else did we sample? I think the optimizer to some extent, the learning rate. But we had to choose a dimension of the hyperparameter space to sample. There was some intuition here building off audit hour that, some had been rolled out as less important. Sorry. Yeah. Oh, sorry. One more point on that. It was intentionally a random, not a Bayesian search, because only then could we really rapidly make use of a lot of GPU hardware to just get a quick answer and beat down the latency.
I'm an ML person, so I'm trying to abstract this into my language. Do you have a sense of how different the training data and the online test data that these models encounter, how they look like, and how it works back with this narrative?
Yeah, what a great question. Yeah, well, so I think you could get a taste for that in this plot, which shows the bias of the online runs compared to the baseline run. And so these are significant biases that the couple simulation encounters that were definitely out of sample to its inputs. And you could imagine them intelligent things to do to expand the training data set with foreknowledge of this halo. I don't think we could have done that earlier because this halo was so wiggly that we didn't know what it was, but that's an opportunity that's emerging. Yeah. Galen?
Yeah, I was going to ask a similar question, kind of how much does this sort of sensitivity of the setup of the algorithm make you worry about its potential generalizability to new climates, new environments, right?
Yeah.
And I guess the idea is to expand the training set, try to make it work.
Yeah, I generally am more attracted to the interpolation limit to try to find a more diverse training set that spans climates. I've thought about doing janky things like maybe our training simulations should constantly have bombs going off in them just to seed a bunch of diversity we don't expect to encounter, but to provide some guardrails to learn the corrective response. And that would be fun to try at some point. Yeah. I think there's a nice paper by Tom that's on arXiv as well that looks at adding physical renormalizations that are strategic to the input vector that try to turn the extrapolation into interpolation across climates, which you can do to a degree, and precedent that things like the relative humidity input definitely expose you less to out of sample error and do provide a bit more generalizability. But I think we have to demand an extreme amount of generalizability to thwart the many degrees of freedom with which coupled errors could manifest. I mean, yeah. Another comment on that is that these statistically steady aquaplanets may not be diverse enough. Maybe their idealization's attractive by virtue of less complexity, but their lack of variability may be unattractive by virtue of less opportunity to learn diverse situations. Yeah. Yeah. Okay. So, okay, let me resurface a little bit with some outlook here. We've talked about some of it, but yeah, one headline is, yeah, this is an old problem now that's getting a bit mature, and it's still a tough nut to crack, at least to have reliable, reproducible, skillful emulation of even this very simplified nesting of convection. So, let alone trying to machine learn an actually spatially explicit region of nested convection. We need to solve this before we can move there. Right now, if you ask me, my opinion's changed over time, but right now I feel like we're missing something in the design of the problem, maybe something in the data that we should have saved that we didn't. I know we forgot ozone. What else did I forget? In full complexity climate models, it's really hard to rule out that some causatively relevant input vector. I've been with this climate model for a decade. I thought I knew it well, but I still surprise myself. I think it's hard enough that it's worthy of a benchmark data set to scale it to our machine learning colleagues, in the sense that ImageNet has had a huge influence on rate of progress in image recognition. So it's time. We're trying to do that now. So Sungduck led the charge to team up with these two guys who are the lead developers of the world's best multi-scale modeling framework now. The only one that an actual climate modeling agency is invested in, the Department of Energy's E3SM MMF. It's got lots of bells and whistles, but most importantly, they know how to go through this code with a fine-tooth comb because they wrote a ton of it. They had to refactor all the data structures to get this thing to run on GPU. And so they're in a good position to make sure that all the data flows across the code regions that we're trying to emulate can be saved in a refined attempt. Okay, so it's time to make a new benchmark that we know is causatively complete. And we've been working hard on this as part of LEAP. I'm excited, we've got it now. It's about 50 terabytes. It's going to be the focus of the summer's LEAP RU students. It's got a hierarchy of complexity. So there's a coarse resolution option that's not too disk intensive, maybe a terabyte. You could subsample it more, or a higher resolution one that's a bit more ambitious. There's an aquaplanet version that doesn't have much variability or continents. And there's a real geography one that does, and it's got seasons. There's about 10 years of output for each time step level output. There's the opportunities to close budgets and draw lots of physical constraints, really rich data set. It's got, for the first time, all the inputs and outputs that are needed to both couple from and to the land model. So we found the packages and the containers that explicitly send information to and from the components in the model and made sure we got all of them. Yeah, so we're planning, we're hoping, we're working right now to try to train baseline models on this new data set. And the goal is to submit a data publication. And this is a big team effort. And if anyone wants to get involved and stand up baseline models, you're part of LEAP, let me know. Yeah, this is going on right now, but there'll be more hackathons. I think we can announce around it soon. Yeah, and I guess I want to conclude this segment about my obsession with multi-scale emulation by saying it might seem uninteresting because the convection is obviously not realistic or important to people. Convection, who cares about 2D convection hiding in a locally periodic array, right? Sure, people care about high resolution and impacts on the scales that matter to them, but that's not real convection, right? But it's a fine place to stop feeling because it includes enough of the complexity of the problem, the stochasticity, the microphysics, the radiation, the convection, that it's hard enough. But it excludes some other things that are even harder. So like another thing you can do is coarse grain, uniformly resolved high resolution models, but there you've got a non-locality problem to worry about. You don't know where to draw the spatial filter. Here we know because it's engineered in the host model itself. And so the coupled test is much more readily approachable in a super parameterized model. So I feel like if we can stop failing on this, then we'll open the door, as ImageNet did, to a bunch of richer applications we actually care about, because there are systems of nested complexity in the climate that we can't afford to resolve that are climate critical, like low clouds, but also like phytoplankton communities that interact with plumes of turbulence, and the details of the turbulence matter in terms of how the nutrient pools that limit the ecosystems and their competitive dynamics interact. That's nested complexity. There's ice sheet calving zones, where the details of the coastal topography really matter to the constraints on outflow and melting rate of the Antarctic and Greenland ice sheets and their consequent contributions to sea level rise. Those are locally nested physics. The details of water management and estuaries that happen, and the spatial details here really matter. So if we can stop failing on this problem as a community, then maybe we can start doing things that will really matter, like machine learning the perimeter of a region of actually geographically explicit high resolution physics. And maybe even sparsely super resolved diagnostically, a subset of the interior resolution where the infrastructure and the vulnerability lives. So yeah, so that's why I'm still interested in this problem, and I hope we can compete on it. Okay, so I'll pause there one more time because we have 10 minutes here.
13, let's say.
No, we're not going to pause then. All right, because this might take longer than I think. Okay, so I'm going to switch hats now. We're going to talk about NVIDIA. I've been having an unexpected year working with an amazing tech company. And what I mostly want to tell you about is the revolution in AI weather prediction, because they built this thing that I think is kind of amazing. Here we go. Okay, so context here now, switching from climate to weather. Weather also takes a lot of computing because you've got to do two things: initialize, and we don't really know the initial conditions, so you need a lot of uncertainty to sample here. And then you need to do a probabilistic prediction where you do many simulations of the next several days to get some halo of forecast uncertainty and a probabilistic outcome to plan around. And these things have always been in tension computationally. You'd like to have more ensemble members because you'd like to have the tails of that PDF better resolved for hazard. But you'd also like your forecast to be high resolution to resolve the hazards themselves, like tropical cyclones, which take a lot of grid resolution. So there's a computational constraint here, just like there is for future climate simulation. Now, I'm not going to talk about hybrid AI simulation now, where you've got a nested AI model that has to interact with explicit physics and all the problems that can happen there. This is just pure machine learning. So AI weather prediction is like video prediction, is treating the weather data as an image and trying to predict the next 6 hours image. Except instead of the image having 3 channels RGB, it's got lots of channels, temperature, wind at different altitudes. But it's the same game. And it's an autoregressive game. So you have one model that just learns the mapping from time step 1 to time step 2. We're going to use 6 hours as the spacing here. And then the outputs inform its inputs, and it autoregressively rolls out until at some point the imperfections of the fit pile up and thwart you, and it goes off the rails, as you should expect. Yeah, and so unlike video prediction, we don't have the whole internet to train off, but we do have 15,000 days of satellite observations, which is pretty good. And it's turned out, and there's evidence in the last 6 months that even small teams of deep learning engineers at tech companies that know how to scale big enough models to big enough volumes of data can stand up these sorts of weather prediction models, and they're producing skill gains rapidly. So at NVIDIA was one of the first to do this with ForecastNet at ambitious resolution. So using the full 25-kilometer resolution of the Era 5 reanalysis as the training data. This is JD Pathak, who I'm totally honored to have on my team, who wrote a great paper or on arXiv where you can read about the model. It's got 1,000 pixels, so you can't use transformers like in large language models where the sequence length is more like 4,000. That's kind of a hard limit to get past. This is like 1 million. And so instead, what we use is a Fourier neural operator, which gets around the quadratic scaling of transformers by using Fourier modes to do the spatial convolution. But it looks like this. Inputs come in, the model predicts the same inputs, the same state vector at some time step in the future. And then, yeah, we train it. And then we do a first stage of training, and then a second stage of training that expands the time horizon of the discretization, doubles it. And you can get skill gains by increasing that time horizon. Yeah, it's about tens of terabytes of data, a fraction of what's available. We use just a few variables on a few pressure levels spanning the atmosphere, winds and temperatures at a few pressure levels. Yeah, maybe that's all I'll say about that. This is what the architecture looks like. It's like a transformer model that uses Fourier modes inside of it to do. We don't have to talk about this, but let's move on to the results. Yeah, so this is the key point though, is it's a global weather prediction model that's fully AI, that's got 25-kilometer resolution. You can initialize it with even with real-time GFS conditions, and this is the key point. It runs. You can run a 2-week forecast in 1/4 of a second, which is 10,000 times faster than classical weather prediction. It's like a totally new limit of computing for the atmosphere. Fascinating. Fascinating only if it produced skill that you believe. Skill's easy to measure. We've got good metrics. So this is the anomaly correlation coefficient. You expect it to decrease as the memory of your initial conditions is lost in a chaotic system at a particular time scale. Yellow is the gold standard benchmark from the European Center for Medium Range Weather Forecasting, which has some of the best medium range forecasts in the world. And the goal of weather prediction is to try to push these curves as far to the right as you humanly can. And so this is where ForecastNet was a year ago or a year and a half ago. And in just a few months of deep learning engineers twiddling knobs and doing other things, we're getting skill gains like this. And it's moving very quickly, I can tell you. And other teams at Huawei and DeepMind have produced preprints in the last 6 months that claim that they're beating classical deterministic forecasts now. It seems like this is the year that AI weather prediction is surpassing the skill of classical weather prediction. Yeah.
All right, you've trained it on a weather prediction, you're not training it on observations. So how can you tell whether it's better than the training data?
Oh, thanks. Yeah, thanks. We're training it not on a weather prediction, but on an assimilated state, which is a fusion of a weather prediction system and an observing system that creates a best state of the observed state of the atmosphere. And it's an uncertain state, but so what we're holding it accountable to in this picture are retroactive hindcasts against that same observed state. Did I answer your question?
So it's the analysis, it's not the.
It's the analysis. It's not trained on the forecast. It's trained on the estimate of the state.
And you're doing an individual tuning to the 6 hour, the 2 day, the 5 day, the 7 day forecast?
No,
Or
we're
are you
choosing an
using the
individual
6 hour
time
and then
scale.
just going forward
Yeah,
6
we're
hours?
choosing a time scale, a discretization time scale, 6 hour in this case. We've tried 3 and 2. You can pick your number. You expect some trade-offs there. You expect the noise to pile up faster if it's a shorter time scale. Yeah.
Okay, so your 5 day forecasts are 26 hour forecasts strung together.
Our 5 day forecasts are the same machine learning model, the same mapping, doing time 0 to time t 6 hours, 12 hours, 18, rolling out. Its inputs are becoming its outputs. It's rolling out. Yeah. And yeah, I want to make the point that it's the speed change that is the significant thing here, because it's just a completely different, it's 4 orders of magnitude. It's 10,000 times faster once trained. So that tension I mentioned between resolution and ensemble size is gone. Once trained, an AI model has fixed resolution, but it's trivial to inference. And so you can think of things like massive ensembles, 10,000 member ensembles, as long as you can deal with the output. But the stuff lives in memory, and you can pipe whatever subset of output. Stakeholders only ever care about a subset out the machinery in intelligent ways. Yep.
So sorry to be the only person asking
No,
questions.
please, yeah. I love
How do you generate an ensemble?
it. Let me talk to you offline. I'm not going to talk about ensemble results here, but I'd love to talk to you about that.
Yeah, because the ensemble in the forecast system comes because it has a chaotic.
Yes.
Right.
Yes.
Is the machine learned?
Yeah. Is it a chaotic
Is it-
dynamical
is it
system?
chaotic in
Yes.
and of itself?
Yes, it is. Yes, it's remarkable. So I should mention that NVIDIA Earth 2 project is closely advised by Peter Bauer, Peter Dubin, some of the top weather forecasting centers leaders in Europe. And of course, the first question they asked is similar. What's your CRPS? Can you get a reasonable spread skill ratio from an ensemble forecast? Mission critical questions to answer in weather prediction. Spread should increase at the same rate as error. And it's interesting to note in operational weather forecasting, because they're computationally limited, you have to go to great lengths to achieve these sorts of goals. You have to find your singular modes to spend your 50 ensemble members most strategically on the singular vectors that will grow fast enough to counteract the underdispersive nature of typical classical deterministic forecasts. In machine learning, you may happen across those modes in a massive ensemble, but we're just at the dawn of ensembling AI machine learning weather prediction. Yeah.
Yeah, I have a related question. So this model is run a resolution of like 25.
Yeah.
And that means that you don't have any subgrid scale, right?
Yeah, there's no subgrid scale. Yeah.
It's sort of like, I don't know, perspective. Like, I feel like it should not have the whole feature space like reproduced anymore. Like you have to miss some part of the feature space. Right?
It's the model I've described is never going to simulate a mesoscale convective system or a severe convective event that has a life cycle less than 6 hours and a spatial scale less than 25 kilometers, because the data doesn't exist. I don't think it needs a subgrid scale scheme to correct it because it's trained on assimilated observations that include the unresolved subgrid physics that normally are a challenge to represent deterministically in climate models. But yeah, that's sort of the limit. Yeah.
Could we then say that it sort of learns a correction from subgrid scale and somehow apply that to predict the future?
You could think of it that way, I guess, if you wanted to say that your typical mapping in a deterministic forecast has to have a divide between dynamics and physics and a representation of the subgrid scale that's part of the overall mapping. There's no such separation in a data-driven model because it's just the outcome of all the physics that informs the best estimate of the observed state that's ultimately the information source for the dynamical mapping. I sense I'm not fully, yeah. Can we talk offline? Okay, I just realized I'm running late. I love these questions. It's like the best. This is Bill Collins, world famous climate modeler, helped write the NCAR CSM, or like its first open source version. He's been working for like a decade just to try to characterize extreme events in the current climate to better understand them, to understand their climate drivers. And he's recognized that this is a great way to bootstrap the observed record to create, 10,000 counterfactuals of extreme events if you believe it's internal variability. So that's what we're exploring together. And his hope is that we may understand the probabilistic mapping between climate drivers and extreme events in the observed record without going to future climate to help us build a better framework for understanding future climate extremes. And I'm really excited about that. Yeah, and then I want to conclude with just some hot off the press recent developments that I think are really exciting that you'll be hearing more about soon. So I mentioned the fact that machine learning models will blow up inevitably, right? And because of imperfections. And I just want you to take this in. This is the Pritchard model, and you'll see it blow up. And this is our new model that has actual spherical geometry in it. And there's your blow up. It's after about 2 weeks. 2 months. We're into two months here. It hasn't blown up. I really did not expect this, really interested in it. And so a tool to share, open source tool that's driving this is a nice, oh gosh, what is going on? There's a nice PyTorch library that's open source with MIT license that has good GPU optimized, really fast spherical transforms that underlie this. So you can check that out if you need such a thing. It's fully differentiable. And our new model uses spherical geometry and relies on these spherical mappings in the interior rather than a 2D FFT that makes inappropriate assumptions about periodicity across the poles. And is probably a better way to think of doing your global convolutions. And it's just that step of respecting spherical geometry in the machine learning that's led to this new capability to roll out months and months and months so far. And so I'm just kind of frankly amazed that this is possible. You'll see secondary tropical cyclone genesis months into the simulation, which I think you ought to be spooked exists in a model with a 6-hour time discretization. These are different fluid dynamics. These are sparsely learned hidden dynamics that are unfamiliar and fascinating. And therefore, there's many, many, many questions we ought to be thinking about, including the great ones about ensembles and to what extent they represent chaotic dynamical systems that we think are appropriate chaotic dynamical systems. And that's work I hope we can do together if you're interested too. It's all open source. You can check out the original AFNO model. It's downloaded from GitHub. ECMWF's inferencing it, NOAA's inferencing it. They're looking at real-time forecasts right now. And hot off the press a week ago, the spherical version just went open source. Hoping to keep open sourcing these things. You need to be working closely with the community of atmospheric science domain experts to be scrutinizing this technology. There's few climate people inside NVIDIA, and if you're interested in using these together, let me know. I'd love to talk. And you can also tune into a White House Presidential Council of Advisors briefing. This is Anima Anandkumar, our unbelievable director of machine learning research, who'll be sharing some of these updates and a few more at 12:15 Eastern tomorrow. So yeah, I'll stop there and thanks so much for your time. And yeah.
You are training your model using a data set
Maybe a little.
and
Just so people online.
so you are using your model, you are training your model, you are teaching the model using an existing data set, a real time, but that depends on how it was accomplished, right? Where the points of measurements were made. Plus, you have some equations, right? But there are equations in meteorology, right?
Yeah, the model I
That-
described does not use equations to produce its forecast, although the data that it is trained on involves an assimilation between a numerical model with equations and an observing system.
Yes, because you plug in the real time initial conditions in those equations.
Yes, since it's a machine learning model, instead of plugging them into equations, we feed them into the input of a giant transformer model. But otherwise, yes.
But you have to teach the transformer
Correct.
how to
Yes.
do
Yes.
this transformation.
Yes, correct. The extent of things that can be learned by the machine learning model, like any machine learning model, is limited by the data set it's trained on.
Yeah, this one.
I see. Yes, yes, that's correct. Yeah. And there are many forms of data one could imagine training these sorts of models on. I've mentioned weather, but I didn't mention what we want to do also, which is to teach them to learn climate projections of the future, which have similar data formats. And if successful, could also provide very low latency ways to inference and reproduce the essential characteristics of climate simulations that maybe help us analyze them more easily, may also be able to generate more realizations of internal variability than are available in climate predictions. There's a lot of things we'll need to work out for that to happen, but we're exploring it.
Any other questions, maybe from early career scientists, especially?
One question regarding climate tech in general. So like, is it safe to make an assumption that this field will be growing continuously in the future? And like you showed some applications of AI, so we'll have more coming up with the coming years, especially with carbon emissions increasing and the rise of EV vehicles, especially in those type of areas.
I feel less qualified to answer your question than at least two people in the room. I'm thinking, Pierre, you sent a slide about this. Ryan is in the back. I know he's investigated the climate tech industry. So is it safe to assume the climate tech industry will be growing in the future? I feel, I'm not a business person. I've been wrenched out of an academic lab into an interesting tech company. I don't know the answer to your question, but it seems like a lot of things are pointing that way.
The summary I had was it was the number 2 in terms of growth after AI. So climate tech was second. Yeah.
Number 2.
Number 2, yeah, in the industry.
I think that was interesting. You showed a little of the work you're doing with Bill Collins. I was wondering if there's any results from that yet, and you're able to see, like doing some hindcasts on things like the Northwest heat wave and some of these crazy events we've been having that are also certainly dynamically driven, how the AI is doing with that.
Yeah, we're on the same wavelength. Yeah, we're spinning up on that right now. Yeah, but this is a new collaboration, just been resourced. And yeah, I could talk to you. Are we recording? Talk to you offline about a couple things. Yeah.
Thanks.
Let me just check with the early career.
So great talk. So one question. So most pure data driven weather forecasting model, they do pretty good job at the like a very short range weather forecasting. So do you have any idea on how to improve the long range predictability in the future?
So I've showed you that reformatting the AI to be equivariant under spherical transformations has made a big deal for us. Anecdotally, Dale Duran's reported the same at UW. I know he's very enamored with the Hillpix grid in astronomy right now because it happens to be amenable to convolutions that obey spherical equivariance. So that's a sample size of 2, but I would say not incurring inductive bias that due to having a machine learning algorithm be inconsistent with spherical geometry seems to set you up to fail on short timescales. Yeah, and I guess I should say, I think Dale's work is very interesting. If you're interested in this, check out Wien et al. 2021. They have a coarse resolution version of something like this that has a seasonal cycle in it that doesn't look terrible, alongside medium range weather predictability and some S2S that's not far from ECMWF's S2S ensemble.
So have you tried this out with a different climate state plucked from a climate projection? And does it kind of revert to the mean, or does it stay in that same climate?
I don't know how much I can say about that, but yeah, I'm definitely interested in that question. To me, in as much as I feel like in my super parameterization work, I want my training data set to span all climates I'm interested in inferencing. I also view this technology as being most appropriately trained in that way. And so for future, I do think there's an extrapolation boundary to the extent it has learned some physics that's worth defining, and don't expect it to be very large. And so my main goal in using tech like this for climate prediction is just to use it as an interpolator and memorizer of existing climate projections. And Bjorn Stevens, who's one of our advisors, is very passionate about that as a way to just reduce the clunky barriers to getting all the rich spatiotemporal detail out of climate data archives. Yeah, the active compression can seem like a boring engineering exercise, but I think it's actually remarkably enabling.
Yeah, I have lots of questions, but one of the ones was like, how much is explainable AI coming into this, and like how much can we learn, right? Are we just going to learn the same things? Are we fundamentally going to learn more because we have an ensemble of 10,000? Is that's the idea, just the better distribution, versus are we going to just uncover all the uncertainties in the fundamental model on which this is trained, right? Like, so do we have an opportunity to learn something about the real climate system here? Yeah, what's your perspective on that, I guess?
Yeah, I'm leaning into both like sort of applied applications here that aren't about fundamental understanding, right? Like reducing latency of climate prediction access, achieving better skill in weather prediction, not trying to understand the sources of skill. I do think you could think about the fact that these are differentiable, and that one of the ways that people have tried to understand sources of S2S skill is by spending a lot of human effort to build an adjoint and to use the adjoint to understand once you've gained a skill anomaly where it came from. So I could see if we pass a important S2S milestone, that being a little easier to approach and maybe resonating with your interest.
There was a question online. Could you comment on how we could improve numerical weather prediction using ML?
Well, yeah, if you believe that what we showed is might be the future of weather prediction, then maybe the role of weather centers should be to your point, enrich the available data record, and yeah, I think I don't know. I mean, far be it for me to say what a numerical weather prediction center should do, but I think the data that they've produced is invaluable and is a government-enabled common good that has enabled all of this technology. And the data is imperfect and depends on sparse sensor networks, and it will only get better with better sensor networks. So to the extent all of us agree that machine learning methods are limited by the data set they're trained on, I feel like this is should re-embolden us to think about how many more measurements we could be taking, or how we could be making better use of the measurements already available. I've only talked about training on Era 5, and of course there's much more out there.
Any more questions? Oh, we have a lot of them.
Maybe following up on that theme, have you looked at, I mean, these are of course the frontier problems, like these are as hard as they get, and they showcase like the best of both software and hardware, but like maybe I guess a different kind of problem, like modeling, say, distribution of clouds, or like something more stochastic as it evolves over time. Is that something that you are interested in as like you, Professor Pritchard, and then you as NVIDIA Pritchard?
Yeah, on both fronts. I would say for the hackathon that we're about to stand up, I think it'd be great to explore stochastic generative methods for it. Gunnar Behrens, a student that Kara's worked closely with through the UCI project, has gone a step in that direction. It seems very promising. The data set that we've got, I mean, it is stochastic data. It ought to be held accountable to stochastic metrics. You could use, generative methods like diffusion methods or variational encoder decoders there. And then to your question about clouds, I wanted to share, I've got to remember his name, but I'll send it to you. A guy at the University of Hawaii I met at a workshop at UCI a couple of weeks ago that was doing lovely work with diffusion models to do exactly what you described, to kind of predict the stochastic spatial detail of cloud fields in a regional scene over Hawaii, trained directly on satellite observations for solar energy forecasting. I think that work's already around us, and there will be more of it. And it's one way to think about achieving the resolution humans care about, despite the 25-kilometer footprint of the data I described, is to tack on generative super resolving models. And I do think those should be stochastic models because, of course, those timescales are quite stochastic.
I was wondering about some of the work from Jerry that you showed about hyperparameter performance online versus offline. Do you kind of see anything in the more skillful hyperparameters that you think iteratively could lead us to select better hyperparameters from the offline training?
I love that question. Yeah. I feel so ignorant in the dark ages when I do hyperparameter tuning because it's just pure random. And I'm sure that's not how card-carrying machine learners would do this, right? I'm aware of such a thing called like a machine learning task with a downstream reward that's not differentiable. This is an example of one. And maybe there are clever MLP models that could be helping us understand the answer to your question about how to more strategically approach the hyperparameter space by feeding off of the large samples we're starting to stand up that contain enough signal to train them on. Yeah. That would be fun to check out. Yeah.
So
We have one question online from George. Are you working on testing on probabilistic scores such as CRPS?
Yeah, absolutely. Yeah. Yeah, I didn't mention that for super parameterization, but yeah, certainly in the weather prediction world, everything's moving in that direction. There's a preprint you can check out from NeurIPS in the fall, Andre Grabner et al. 2022, that shows with a bit of brown noise perturbation into the initial condition, we can get a reasonable spread skill and a CRPS result. I think it's early days there. Yeah, I think Dale Duran just exploited the existing initial perturbations from the UCMWF, which has a limit of an ensemble size. So if you want to perturb a 10,000 member ensemble, you're going to have to come up with your own algorithm. And yeah, but yeah, CRPS is the important thing to chase. I'm aware that Peter Dubin's been involved in a paper too, that CRPS was directly the objective. Our machine learning model was trained on an L2 loss based on that time-step mapping, but you could equivalently try to train an ensemble to be optimized towards a CRPS, and that may blur your solution, but I think it's quite interesting.
Maybe just before closing, I'd like to ask a question. So do you think we could do better than weather forecasting, because my thinking has been that actually data assimilation is pretty great, in a sense that it's pretty much like machine learning. You have a loss, except that you can be very objective in terms of having an observation operator, right? And we don't have that mindset and that framework currently within the kind of the machine learning toolbox, right? So I was always wondering, can we even do better? We can do faster for sure, but which is great because then you can regenerate also members and etc. But we'd love to hear your thoughts on that.
So DeepMind claims to have done better. You can look at their scorecard. They're beating ECMWF on 90% of their own internal scorecard metrics across variables and lead times. So they would say they're already doing better even without what you described. But yeah, I think there's great opportunities in combining machine learning with data assimilation. I'm aware of at least one NOAA-Google partnership to that effect. Yeah. Am I speaking to your question or? Yeah, I think it's, yeah. But it's like, what a year. This is, yeah.
Maybe kind of relate to that. You still need the initial condition, right? So you still need the model in the end and the assimilation to get started.
Yeah, we should all celebrate the government investments that have produced the data sets from deterministic models and observing systems, which only together produce these high fidelity estimates of the observed atmospheric state. that are worth training these machine learning models against, and that are the source of their skill. And that is a total good that has produced an incredible thing, I think. And how can we make that public good even better? And I want to conclude with one other thing. I'm being wrenched out of the ivory tower now and realizing that in a company, you can maybe make things that people use and have impact. And thinking about data-driven weather prediction is so liberating because you can, as a stakeholder, directly engage in the loss function of a machine learning model. You know, if I'm a person worried about wildfires in California and I want to coerce a deterministic model to become better at them, it's a nightmare, as you probably all know, twiddling parameterizations and hunting for something that may give me a bit of anomalous skill for a subphenomenon. But you can express your preference for machine learning attention to pay attention to subphenomena. I think that's liberating, interesting. I haven't seen a proof of concept yet that shows me that it doesn't just trade off against other phenomena in ways that thwart you, but I feel like it's likely possible. And I think there's a huge category of exploration that needs to be done today. And again, a lot of exciting questions. And if trying out the gizmos is a barrier to getting involved and you're motivated to, please let me know, and I'd love to help connect you to people.
So let's thank Mike again. Thanks so much.